Does the series converge or diverge? If it converges, to what does it converge to? So again, quickly before we do anything, we're going to pull this guy out and do a quick divergence test on it. And when I do that, I see that as n gets big, the denominator dominates, so I end up with 0, and that gives me no conclusion. So the divergence test doesn't help me. The terms of the sequence go to 0, so maybe there is hope that this converges. Now, it's not a geometric series because I don't see any form of constants raised to the n. There is a rational expression involved, so that leads me to believe maybe that could lead into some form of a telescoping series. Also, the other thing, if you're leading towards the integral test, this curve will, if you compare it to f of x equals 3 over xx plus 3, it will be actually positive, continuous, and decreasing from 1 on. So it'll satisfy the 3 conditions of the integral test. However, in the process of doing that improper integral, you're going to have to do a PFD, partial fraction decomposition, on this anyway. So might as well analyze the partial sums of this to see if that's going to help me get a closed form for the partial sum. So S sub n will be I equals 1 to n of 3 over I times I plus 3. So we're going to look at 3I over I plus 3 and do a partial fraction decomposition on it. Again, even if you went the integral test route, you would have to do that anyway to evaluate that integral. So we break it up into a over I, b over I plus 3, clear the fractions, and then try to figure out what a and b should be. So once we do the analysis, we see that a is 1 and b is -1. So the nth partial sum can be broken into a difference of these two terms, 1 over I minus 1 over I plus 3. So now I can go ahead and open this partial sum. And since they are 3 apart, keep in mind, if things are to cancel, which they look like they will, probably the first 3 and the last 3 terms will be left because these two I and I plus 3 are 3 apart. But we'll go ahead and open it up and look at a few terms by looking at it with this method first. So I'm going to open up some spaces. I'm just going to choose to go up to 5 and then have maybe like 3 of them at the end too to see what it looks like. Okay, so I went ahead and filled those in, making I go from, actually I have this notation wrong. Let's fix that before we do anything. I'm looking at the partial sums, so I'm stopping at n. It shouldn't be from 1 to infinity. Okay, so I put in I equals 1, and I just chose to go up to 5, and I put one more, n minus 2, I put n minus 3 also because some of these things will actually cancel if you go previous enough, if that's the term to use. So if I'm looking at what's canceling, it looks like this guy goes away with that guy, and then I have anything else. This guy goes away with that guy, and I have what else? Nothing else here with the ones that the numbers that I can see. As far as the n's are concerned, I've gone enough back to see that this will also cancel with this. And again, if I see previous terms, some of these other guys will cancel also. Now, if it's confusing for you and you can't tell which of these should go away and which of them should stay, as I was saying earlier, you can just say, I'm going to focus on 5 or on 4, whatever you want to stop at, and I'm going to see what's left and relative to 5 being my n, for example. So S sub n, again, you want to formally show ... that this thing goes on and stops here. At least show the last term if you're not going to show the previous ones. So show all of that, and then if you focus just your n being 5, you can see that this is left, this is left, this is left. So I have 1 plus a half plus a third, and then in the tail end, this is left, this is left, and this is left. And relative to 5, which is where you chose to stop, what is 6 relative to 5? Well, 6 relative to 5 is 1 over n plus 1 because it's 1 bigger than 5, minus 1 over 7 relative to 5 is n plus 2 minus 8 relative to 5 is 1 over n plus 3. So at the end, if you show enough terms, actually this guy right here will cancel, and this guy right here will cancel as well. And so will the 1 over n minus 3. So ultimately, the nth partial sum is really this. They were 3 apart. The first 3 are left, and the last 3 are left. And the limit, as n goes to infinity of s sub n, we know that this guy goes to 0, this guy goes to 0, and this guy goes to 0 as n goes to infinity. So I just end up with 1 plus a half plus a third, which I guess ends up being, what, 11/6? So the series was indeed a telescoping series, and it converged to 11/6. Now again, if this process right here is confusing for you, you can go take this nth partial sum and fill in pieces by adding and subtracting to creep up one by one from I to I plus 3. So let's go look at it that way as well. So we look at this partial sum and we say, well, I have a 1 over I, and then I have a minus 1 over I plus 3. I'm going to go ahead and subtract and add the same term over and over until I walk up one by one to I plus 3 in the denominator. So I'm going to subtract 1 over I plus 1 to get this to up 1, and then immediately undo what I just did. I'm also going to do subtract 1 over I plus 2, and then add 1 over I plus 2. So essentially, I have not changed the series because I've just added a bunch of zeros. Then I'm going to group and say these guys will act together, these guys will act together, and these guys will act together. So my nth partial sum can be analyzed as this plus this plus the last two guys. And each one will require its own analysis, and it may be a little bit long, but they will be varying by 1, and it might be easy for you to see what cancels and what stays. So let's look at each of the 3. If I look at 1, and I just start at I equals 1, and let's say go all the way up to n and show maybe n minus 1 as well, I will have 1 over 1 minus a half plus, when I go to 2, a half minus a third. When I go to 3, a third minus a fourth, plus dot dot dot. I can go to 1 over n minus 1 over n, and then stop at n if I want. So that'll be the first sum. Let's go do the next one as well. When I is 1, I have a half minus a third. When I is 2, I have a third minus a fourth. When I is 3, I have 1/4 minus a fifth, plus dot dot dot. N minus 1 will give me 1 over n, and n plus 1 for the second guy, and n for the very last stop, 1 over n plus 1, 1 over n plus 2. So that's the second one. Let's go do the same thing for the third one. So I did the same thing for the third one. I equals 1, 2, 3, and then I put n minus 1 and n for my last stop. Now let's go analyze each one. So if I'm looking at the first one, it's very easy. These guys go away. These guys go away. This must go away with the next guy. This will go away with that, and this must have gone away with the previous guy. If I look at the next one, these guys go away. These guys go away. This must have gone away with the next guy. This goes away with that. And this guy must have gone away with the previous guy. Last one, this goes away with that, this goes away with this, the negative 1/6 must go away with the next guy, this goes away with that, and the 1 over n plus 1 must have gone away with whatever was before it. So ultimately, I am left with what terms? I have this and this for the first one, this and this for the last one, or second one, and this for the last one. So I am left from the 3 pieces with 1 minus 1 over n plus 1. And then with this guy, a half minus 1 over n plus 2. And with this guy, a third minus 1 over n plus 3. And I'm adding all of these. So my nth partial sum is really these constants at the beginning, and those same last three guys that were left from before, and again, the limit as n goes to infinity of s sub n, these last three guys will go away and we'll end up with 11/6. So the partial sum that we got with this process, which does seem longer and more expansion, is the exact same partial sum we got the other way. But the second method may be easier for some of you because there's nothing being skipped and things are just canceling right next to each other. So it was a telescoping sum which converged to 11/6.